Hello everybody. Today we're going to look at a problem where we have two different phases. Both phases are going to have some acceleration. So in the statement we're told that a model rocket is shot straight up into the air and it accelerates from rest with a known acceleration. After 3.7 seconds, a fin gently detaches. I'm using that wording only because I really want to stress that somehow this thing comes off of the rocket. It's going to behave initially however it was behaving when it fell off the rocket, and then it's going to go into a second segment of free fall, and it's going to come back down to the earth. In this problem, we are certainly going to ignore air resistance. I would envision that being really important if this happened in real life, but we're going to ignore it in this problem to simplify things. But the overall question I'm asking is, how long does it take for the fin to hit the ground after the initial launch? Just to make sure everybody is understanding what this problem should look like before we actually start solving it. I think I just want to graph it here. So if this is the height, so I'll use a d for displacement, but if this is essentially the height of the object and this is time, we have two phases. Initially, we're going to have a positive acceleration that is a concave up parabola. So this coefficient here, if that thing is positive, you are concave up. So that was an upward scooping parabola. So this thing is going to have an initial velocity of 0, and it also has an initial position of 0, and it's going to go whoosh like this, upward scooping parabola. Then at some point it detaches, and the rest of the problem takes hold here. And so this is the rocket going up, and then at this location right here it detaches. Well, remember that if the rocket was traveling up with a particular velocity and the fin comes off, that fin must also have that same common shared velocity. And so it's going to continue going up for a little bit, but it is going to eventually undergo the effects of gravity, and it's going to be pulled back to the surface of the earth. And so you can see here the two different segments. We have this rapid upward acceleration, and then we have this new situation where the fin is going to go up for a little bit, hit its highest point, and then it's going to come back down to the ground. So with that picture in mind, let's go ahead and do some calculations. I want to reinforce writing functions on this particular problem. So this is the function that describes the displacement of an object when you do have constant acceleration. We're going to use that two different times in this problem. So for the first segment, that is the upward acceleration. The rocket is going, the fin is still attached. I'm going to go ahead and write in the things that I know. I know the acceleration is positive 22 meters per second. That was told to me in the problem. So instead of 22 meters per second squared, what I'm going to have is half of that for the actual function. So d as a function of time is going to be equal to 11. It has those same units, meters per second squared, but I'm going to leave them off, times time squared, plus, and then the initial velocity of the rocket, well, it's sitting on the ground at rest, and so that's actually 0 times time. This whole term is going away for us, and plus the initial location is still sitting on the ground, so another 0. So this equation actually simplifies quite nicely for us to just be d of t, the position of the rocket as a function of time, is 11t squared. And in this problem statement, I am told for how long it is going to accelerate up before this fin actually detaches. So I can plug in that particular time. So d of 3.7 seconds is going to be equal to 11 times 3.7 seconds squared. The units in this would come out to be in meters, and I will find that d of 3.7 is equal to 150.59 meters. Okay, so that is the height of the rocket before the fin actually comes off. And now that's a really important number for me to know, because now I'm going to move into the second phase here. So over here for the second phase of this problem, I'm going to rewrite a new function. So that function no longer describes the fin. I need a new one. I'm going to come over here, and again I need to fill in this coefficient. I have d of t is equal to, Now I have 1/2 the acceleration. The acceleration here is going to be negative 9.8 meters per second squared because it's in free fall. So half of that is going to be negative 4.9. No units. There are units, but I'm leaving them out. T squared plus the initial velocity. Well, what is the initial velocity of this fin? It is not 0. It is whatever the velocity was of this particular rocket at 3.7 seconds. That's where this is going to come in really handy. So let's come down here, and I'm actually going to grab a new marker. V as a function of time is acceleration times time plus VI. Now I'm doing this for the first scenario again because I'm trying to find out something about the rocket in its initial flight. The velocity of this thing as a function of time is going to be equal to, again, its acceleration, not 1/2 of it this time, but the full acceleration, times time plus the initial velocity, which was 0 for us. Okay, so there was no velocity. That means I can find that the velocity at 3.7 seconds was equal to 22 times 3.7 seconds, which is equal to 81.4 meters per second. So that is also a valuable number. Now that we figured that out, I probably should have just figured it out before. I need both of these pieces of information to fill this remaining function out. So now I'm coming over here again, and I'm looking at the free fall of the fin. I had the acceleration was due to gravity, negative 9.8, so there's my overall coefficient is negative 4.9 t squared, plus 81.4 times t, plus the initial height of it when it starts this phase is the 150.59 meters. So I'm going to clear a little board space, and I'm also going to rewrite that function so it looks a little nicer. Okay, so here's the same function as before. This is only the function for the second part of the trip. But what I need to do is I need to figure out how long it takes to fall to the ground. Well, I have defined the ground as the 0 location for this. So here's the initial start height, well above the ground. So I'm going to go ahead and set this entire quantity, the left side here, equal to 0, and write this out one more time. And you will see that I've now set myself up for using the quadratic function to solve for this. So plus 150.59. After using the quadratic formula, which I'm not going to show all the work for here, I'm just plugging it into a program for it. But using the quadratic formula always gives you two solutions. The solutions I get are t equals negative 1.68 seconds. And I also get the other solution of 18.29 seconds. Now, one of these makes sense and the other one doesn't. The negative time is not valid. It's a valid mathematical solution for this function that I have here. However, it is not the one that is of interest to me for my particular problem. So this is how long it takes for the fin to fall to the ground. Remember, it has to go up a little bit before it comes back down. But the overall problem says how long does it take, what time does the fin hit the ground after the initial rocket launch. And so I have to come up here and modify that answer that I have down there by this 3.7 seconds number. So I'm going to have this number that I just found plus 3.7 seconds from the original upward launching, and that's actually going to round to pretty close to 22 seconds. And that is my final answer for this one. Hopefully that problem made sense to you, and if it did, let your computer know.